So in the previous video, we took a look at the mechanism for radical halogenation of methane, or radical chlorination of methane. And really all radical halogenations follow this general mechanism. And just to review it, I'm going to review it here. So you have this initiation step, which is just the furnishing of the chlorine radical. Remember, homolytic cleavage. This dot should be representing a radical there. Then you have two propagation steps, which work in tandem to form your product. Your both HCl, your products HCl and chloromethane. So the first, propagation 1, chlorine radical reacts with one of the hydrogens in it combines with one of the hydrogen atoms in methane. You get HCl, and you get the methyl radical. And then you have propagation step 2. And that's just where this methyl radical reacts with diatomic chlorine. So everything here is homolytic cleavage, so only movement of a single electron, not a pair of electrons, to get chloromethane and chlorine radical. Remember, this chlorine radical here can be reused in propagation step 1. And of course, or as I said in the prior video, this basically continues until a chlorine radical bumps into another chlorine radical. So it continues until you have a chlorine radical bumping into another chlorine radical, or a methyl radical bumping into a chlorine radical, and that'll actually give you the major product here. Or two methyl radicals bumping into each other. And any of those two, if any of these three things happen, you will get a termination of the reaction. But what if we're interested in the rate of the reaction? Well, it turns out that the reaction rate is proportional. This just means is proportional to the product of the concentrations of methane and chlorine radical. So another way of saying that is the rate equals some rate constant K times the concentration of methane times the concentration of chlorine radical. And this basically shows you that hopefully you remember that from your general chemistry classes, that the rate is, you have a rate law written like this. You have K times the concentration of a reactant raised to the power of its coefficient times the concentration of the other reactant raised to the power of its coefficient. And you can see here that in propagation step 1, the reactants you have are chlorine and methane. So the reaction rate is equal to the rate of propagation step 1. So propagation step 1 is really the rate limiting step. So propagation step 1 is the rate limiting step. Okay, so let's let's draw a reaction coordinate diagram for propagation. Step 1. And that's a step where you get the methyl radical, right? So this is propagation step 1. Chlorine radical reacts with methane to furnish methyl radical and hydrogen chloride. So we write the reaction coordinate diagram. We'll have enthalpy on the y-axis, or the vertical axis. Let's have standard enthalpy, and one second. There we go. And we'll have reaction coordinate on the x-axis. So the reaction coordinate, basically it's the position you are in the reaction. So on the left you'll have reactants, then you'll have a transition state, and then products. Okay, so here you'll have methane and chlorine radical. You'll have the transition state. You'll have the product. Delta H for this step here. This delta H. This delta H is plus 2 kilocalories per mole. So this is the product here. So this is plus 2 kilocalories per mole. And the activation energy to reach the transition state, remember, it's denoted E sub A, and that's just the energy difference, or the enthalpy difference between the reactants and the transition state. In this case, it's 4 kilocalories per mole. And the transition state, let me draw the products here. So the products are here. Going to be methyl radical, CH3 radical, and HCl. But the transition state's basically a state in which this CH bond is partially broken and the bond between hydrogen and chlorine is partially formed. So this bond will be partially broken, and you'll have partial binding to the chlorine. So it's kind of, you can think of it as halfway between your reactants and products. It's not necessarily halfway. It depends on whether the transition state's an early or late transition state. That's basically whether the transition state more resembles the reactants or the products, but we'll get into that in a future video. But it's basically, it involves partial breaking of the bond that's broken in the reaction and partial forming of the bond or bonds that are formed in the reaction. And the energy difference between the reactants and the transition state here is 4 kilocalories per mole, and that's called the activation energy. It's denoted E sub A. This is the activation energy. Hopefully you can read that. So this step here is the slow step in the halogenation, in the chlorination of methane. And so the reaction rate is determined by this step. If you remember, I said the reaction rate here is K times the concentration of methane times the concentration of chlorine radical, which are the reactants in propagation step 1, and that's a step for which we've drawn this reaction coordinate diagram. You can see it is an endothermic step. The other step is exothermic, so the reaction rate's not really dependent on that. That step will occur really quickly. Now, what if we're interested in the rate limiting step, in the reaction rate for ethane? So we need to figure out what it's in the reaction rate for chlorination of ethane. So we need to figure out what's the rate limiting step in that reaction. So the halogenation of ethane, or the chlorination of ethane, it's basically CH3 reacts with Cl2. This is the overall reaction to give you chloroethane plus HCl. But as in all radical halogenations, the rate limiting step is formation of the ethyl radical. So this, of course, here you'll have initiation, right? To form, you have to first form the chlorine radical, and then that radical is going to react with ethane. So that radical will react with one of the hydrogens here on ethane. Let me fix this real quick. And you'll basically get ethyl radical and HCl. And this is the rate determining step. After this step, you'll have a fast step so this is propagation step 1. Propagation 1. Then you'll have propagation 2, which is a fast step. And that's basically where this ethyl radical is going to react with diatomic chlorine to give you chloroethane. But we're interested in the rate of this overall reaction. And remember, in all radical halogenations, formation of the alkyl radical is the rate determining step. So this is the rate determining step. So the rate's going to be some rate constant times the concentration of each reactant in this step. So times the concentration of chlorine radical and the concentration of ethane. So knowing that, let's draw the reaction coordinate diagram. So you'll have chlorine radical and ethane. I'll write it as C2H6 to save some space as the reactant. And this step is actually exothermic, unlike the case of ethane. This is -2 kilocalories per mole. So you'll have the reactants here. You'll have a transition state. Then you'll have the products. And if I draw a horizontal line, you'll see delta H is -2 kilocalories per mole. What does the transition state look like? Well, what we have to first draw the products, right? So we have HCl is one product, and then you have ethyl radical, that's the other product. So CH2, and I'll draw a dot right there. So the transition state is going to involve a partial breaking of one of the CH bonds in ethane and a partial forming of this HCl bond. So it's going to look something like this here. So this bond is partially broken. This HCl bond is partially formed. And as I said earlier, the extent of movement of H towards the Cl and away from this carbon is dependent upon whether that transition state is more energetically similar to the reactants or the products. In this case, it's more similar to the energy of the reactants, so this hydrogen isn't going to really be moving very far, so it'll be somewhere like here, right? Because this activation energy, I forgot to mention that here, the activation energy is equals 1 kilocalorie per mole. So this is of course it's positive because transition states are always higher in energy than reactants, but the energy of this transition state is closer to this than it is to this, right? If the total enthalpy change for the reaction is -2 kilocalories per mole, you're going up 1 kilocalorie per mole to get to the transition state. That'll mean you're going down 3 to get from the transition state to the product. So this transition state is closer in energy to the reactant. So it's going to be closer in structure to the reactants. But we'll get into that in a future video. But it will look something like this. So hopefully now you have some insight into the kinetics of radical halogenation reactions, and we'll look at chlorination reactions and other halogenation reactions of a variety of alkanes in future videos.